Efficiency Canada's discovery session on Friday at noon or morning or afternoon, depending on where you are in Canada or maybe around the world. We do have some people joining us. I'm Natalie Oren, Director of Stakeholder Engagement here at Efficiency Canada. Welcome. Again, I hope it's now February. I can't believe it already at the same time. It still feels like the same day since last March. Which is very much in line with our topic here today, but I'll get to that in a minute. Just a reminder that to please hold your questions until the end. There's two ways to ask questions. One is you can raise your hand, your virtual hand, and I can unmute you and you can ask your question yourself. The second way is at the bottom of your Zoom screen, you'll find the Q&A box and you can type your question in and I will try my best to narrate that for you. And that's pretty much about it. The only role that we do have is the same one that we have for our presenter is no sales pitches. So that's for all of you people out there, that means no statements disguised as questions. So that is a rule that we try to keep to just to keep it interesting and fun for everyone here that's joining us today. So without further ado, please welcome Josh Lewis from Nerva Energy, who is going to speak to a very, like I said, topical topic today, mitigation of communicable diseases, which includes COVID, spread while managing and enhancing energy efficiency. So I'm really excited to find out how you've looped energy efficiency into this, Josh here. So again, I'm going to let you get started, and I'm really looking forward to this presentation to learn more.
Thanks, Natalie. Appreciate this opportunity and glad to share this information with everybody who's attending this session today. And of course, we're recording this, so it'll be available later as well. Like it says there on the slide, this pandemic has forced building owners and operators to implement strategies to, improve indoor air quality and reduce the risk of disease transmission. But we need to look at that in terms of energy efficiency because, and what are the measures being deployed and what are the positive and negative impacts that they can have on the operation of our buildings and the utility costs. So just to open it up, we need to first understand the total ecosystem of transmission vectors of COVID-19. And certainly these transmission vectors are not unique to just COVID. We have seasonal colds, seasonal flus. But in terms of the risk of transmission vectors, we have person-to-person airborne particles as well as contaminated surfaces. So looking at person-to-person, what do we do to mitigate those risks? Well, we wear masks, we social distance, we've installed a lot of plexiglass barriers in retail locations and offices. We are being forced into small bubbles of interaction so that we don't have a lot of people around us to spread the diseases. And we're also working from school at home. This is the biggest work from home experiment that the world, I think, thought they would ever run, but we're right in the middle of it right now. Some people think it's going well, some people not so much, but in any case. Then we look at airborne particles transmission. And, the mitigation strategies here are primarily filtration, dilution, purification, as well as humidity. Now, that's going to be the focus of this presentation, and that's where we're going to do our deep dive. But the other part is contaminated surfaces. So we've definitely put mitigation strategies into place for these as well. That's cleaning, antimicrobial surfaces and coatings, gloves, as well as hand washing. So all three of these major mitigation strategies are important and we need to do them all. But today we're going to be focusing on that airborne transmission. So when we talk about airborne particles and HVAC systems, transmission is a real concern, especially for COVID-19. It was not fully understood, obviously, at the beginning, whether it was large droplets, small droplets, what the distance and the risk and the time factors all were. But it's been shown now through various studies, data, contact tracing, and even a lot of the data that the NFL has collected. They've collected millions of data points in terms of tests and contact traces, and the CDC just released a paper showing how great the risk can be from airborne transmission. The picture you see there on the right is actually from an outbreak associated with a restaurant in China, very early in the pandemic. And what happened there is one patient came in that night in January infected, And when the people left the restaurant, many people were infected on that one side of the restaurant. And the studies, and there's articles linked in this presentation with further details, kind of are indicating that that EC unit on the wall, which was recirculating air, actually pulled air around that side of the restaurant and infected all those other people from patient zero. Yet the other side of the restaurant, which is really not that far away, there was no infections there that night because the airflow wasn't on that side. So it's data like this, and this was, you know, an early case, but there's certainly been other cases built since then which show just how transmissible COVID is in airstreams and inside interior spaces. Now, you know, there's no single solution to fixing this issue. It's a multitude of things. We're gonna talk about a lot of things today at a high level. But what are we looking to do? Well, we definitely want to improve safety. You can never put a price on the health and safety of any individual. But at the same time, business owners and building operators want to reduce their risk and liability. They want to maintain comfort. And they also want to manage and conserve energy at the same time. So how do we try to achieve all these things simultaneously? So when we're talking about balancing safety and energy efficiency, you know, to mitigate risk while managing at the same time, we have to realize, first of all, that the energy efficiency in HVAC systems has typically entailed items that are not necessarily down the same path as indoor air quality. For example, you know, tight control of temperature set points, both occupied and setbacks. Well, that's something common that we should be doing. Typically, though, basic filtration is the most energy efficient, only operating fans when required, minimizing fresh air intake into the building, also letting humidity levels float, especially in the wintertime. So doing all these typical things is usually what we think of in terms of creating the most energy efficient HVAC system. Now, you know, we can benchmark against hospitals for a lot of this because hospitals have very high HVAC energy use due to the codes and standards developed by ASHRAE, specifically, standard 170. You know, but hospitals have the densest and most energy intense HVAC systems per square meter of building space, really compared to most other buildings, right? Because they have constant volume systems with high fresh air percentages, really tight filtration. So I think we can learn from hospitals and translate that into other buildings, not taking it necessarily to the same level as hospitals. That would be near impossible, but trying to get to that mark. Now, but COVID has forced us to rethink what HVAC systems need to do. You know, we always talk, you know, energy efficiency was the key driver, but now indoor air quality has raised its ugly head, and so it should, because we need to make sure our buildings are safe and healthy, right? We need to effectively remove most contaminants out of the air. We need to keep air moving within buildings. We need to guarantee fresh air exchange rates, and we need to actively control humidity levels. Some of this is you know, part of standard HVAC design and standard building codes, but you know, we've tweaked out maybe some of this over the years in our quest for efficiency without really considering the indoor air quality because it wasn't an urgent concern, but now it is now. But as we go down this path of trying to achieve great indoor air quality while being energy efficient, the benefits are going to be likely above and beyond COVID and the current pandemic. It's going to help us affect seasonal flus and colds, other airborne pathogens. And, you know, this is a good thing, I think. You know, it's going to give us this renewed focus on indoor air quality, health, and wellness, and not trying to sacrifice one for the other. So let's start with filtration and improving the performance of that. So filtration performance is critical, especially on any systems that mix or recirculate air. So this is the vast majority of buildings. So, you know, as you're looking at your current operations, the first thoughts that should run through your head are, do you know your current filter performance level? Do you know your current filter condition? And what is your strategy for changing filters? You know, the MERV rating table for filters is there on the right. And first thing has to be realized is not even all filters have a MERV rating. Media style filters, which are very loose, don't have a MERV rating and are practically useless for COVID-19 or most airborne pathogens. Typical pleated filters usually have a MERV 7 rating, but is that enough? Well, the answer is no. ASHRAE has come out and said that MERV 13 filters are the minimum recommendation for COVID-19. Now, most large air handlers can utilize MERV 12, 13 filters. but we have to realize that high MERV rated filters will need to be changed more often. They're simply tighter, they're more effective at removing contaminants out of the air, but that means they're going to plug up quicker as well. But HEPA filters, which a lot of people are, investigating or installing, especially in HEPA filter carts, maybe side, carts that are wheeled into a room that supplement the filtration of the HVAC system. We have to realize that HEPA filters can't be used on most standard equipment outside of hospitals. So don't think that we're going to go out and buy HEPA filters and install them in our rooftop air handling unit. HEPA filters are too tight, and the fans in most typical equipment aren't designed for HEPA filters for that level of tightness. Also, the fact that HEPA filters, to be affordable in any kind of way, need a pre-filter, and otherwise the HEPA filters plug up too quickly and they're very costly to replace. And typically our air handling systems have not been designed for those. Now, what are the efficiency opportunities here, though, in filtration? Well, differential pressure, DP, has always been the optimal way to evaluate filtration system performance and replacement cycle. Changing filters on a time-based schedule is generally inefficient from one of two ways. Either we're changing the filter too early, meaning that there's still life left in the filter, meaning that we're spending more on filters, or if we're doing it on time, we could be changing the filters too late, meaning that the filter performance is now degraded, the fan is probably drawing more power to draw air across the filter, and we're off the performance curve. So differential pressure has always been the optimal way to determine when a filter needs to be changed. So that is the strategy that should be implemented, whether manual readings, electronic readings, tied into the building automation system, whatever you can do to optimize that. The other part is considering switching to electrostatic filters. This is not new tech, certainly been on the market a long time, but you can get very high MERV ratings on electrostatic filters with very low differential pressures. And electrostatic filters basically use electrical static discharge as the air flows by to draw contaminants to their surfaces. Now, those surfaces do need to be cleaned once in a while, but the airflow is very smooth through them. So they do work at a very low differential pressure. Definitely electrostatic filters are going to have a higher upfront cost, but they are going to cost less to operate over time when you consider that they're going to use less energy on the fan. They're also going to use less, you're not using replaceable media anymore, so you're not going to have that ongoing cost. And these types of filters can be retrofitted into existing systems. So it's definitely an upgrade that can be done in a lot of typical air handling units. So it's something to definitely investigate. Now, the efficiency pitfalls here, though, is, we do need to consider the pressure drop across any filter, whether it's the one we're using or the one we want to upgrade to, because too great is going to drop the air flow, which is not good for risk mitigation, and increase the energy usage. So you got to kind of get a double negative out of that. And only, the tip here is only make sure that you look really intently at the filters with return or mixed air. Don't upgrade the filters on makeup air units or dedicated outdoor air systems that don't have recirculation. Those units are just drawing 100% outdoor air in. Outdoor air we can consider in virtually every case to be relatively clean, certainly probably not infected with COVID. So MERV 7 is fine. We don't need to go to MERV 13 on those 100% outdoor air systems. And I recommend using an HVAC professional to measure fan power and motor, fan power, motor, pre and post filter changes, and assess the airflow balance if you are doing a major filter upgrade to make sure you're not negatively impacting your efficiency or your airflow within your system. Now, next is dilution. We want to definitely keep the air moving, ensure that constant circulation is occurring in buildings when they're occupied. So what does this mean? Well, makeup air systems should be on and running at full speed. That basically means fan on mode, if we think about our thermostats within all zones while the building's occupied. Rooftop and heat pump systems, exhaust, ERVs, HRVs, or VAV or VVT systems, forcing them to move air where they may have traditionally not moved air before in order to get that keep that circulation going to reduce risk. And consider flushing the building by turning on systems early, maybe 2 hours before occupying, 2 hours after occupying, modifying your controls to get that flushing going on to again, keep more air moving, more air filtered, and reducing the risk of transmission. So the real efficiency opportunity here in terms of keeping air moving is installing, upgrading, or retrocommissioning HVAC controls. You want the fans to run in an automated way. You also want to ensure repeatability in the operation and that you're keeping a data trail. That could be very important should, something, get upset and, perhaps there's a lawsuit or you're pulled into a court. By having a great control system, not only can you make sure the actions are happening all the time, but you have that data trail to reduce your liability. And also too, from an efficiency perspective, when the building is not occupied, make sure the HVAC controls are putting those fans back in auto mode to save as much energy as you can, and that they don't start up again until you get into that pre-occupancy flushing cycle. Now, the next part is about dilution, is fresh air. So again, during occupied hours, which are the important hours, we want to guarantee a volume of fresh air should be brought into a building. Now, this may not be always occurring, especially in systems that have CO2 demand control ventilation, right? Typically, those types of systems are set up to bring in only a minimum amount of fresh air or no fresh air unless the CO2 levels in the space in the building rise above a certain set point. 800 parts per million is around normal, can be slightly more, slightly less, but that's pretty typical. So now, right now, until we get mass vaccine rollout and community transmission of COVID drops, we really need to consider disabling demand control ventilation on any systems that we have. Unfortunately, that's not great for efficiency, but it mitigates the current risk. Now, for dedicated fixed volume makeup air for larger buildings or rooftop units with economizer, it is critical to understand the size, setup, and current operation and the maintenance state. I've seen a lot of economizers in my time that fail silently closed. Sometimes they fail open, but a lot of times they fail closed, and all of a sudden you're not bringing any fresh air into the building, whether under a demand control ventilated strategy or even a fixed percentage fresh air ventilation strategy. So inspecting your economizers, inspecting the return mix dampers, and making sure that the system is operating correctly to make sure this fresh air volume coming in is critical. Now, the next thing, and this is something which may be new to a lot of the participants on the line, is ductwork leakage. So all ductwork systems leak, but to be perfectly honest, this is not necessarily common knowledge. But ductwork leakage within buildings impacts both the indoor air quality and the energy efficiency. Now, if we pull a quote right from ASHRAE out of the duct design manual, ASHRAE states that 75% of commercial ductwork systems leak between 10 to 25%. And based on real world numbers that I'm seeing, actually the leakage is typically higher than that, maybe in the 20 to 35% range. Now, what does this mean? Well, that means that we're leaking air from the ducts into ceilings and mechanical spaces, which we're wasting energy to do because those are unoccupied spaces of the building. Nobody's breathing that air. And we're also reducing the effective dilution rate of the entire air system in the building, again, where people are breathing in the occupied spaces. We don't care about ventilating ceilings and mechanical shafts where no one is breathing the air. So if duct leakage is reduced, there'll be an immediately more air exchange in the space that people occupy, reducing the transmission risk. But what are the options to fix this issue? So ductwork can be sealed. Now, the traditional methods during typical new construction projects or major retrofits is using mastic, tape, and caulking from the outside. However, there is newer technology on the market now, which you can seal ductwork from the inside out in a more repeatable, computer-controlled process that is actually a lot quicker and a lot invasive to buildings, especially existing buildings. So this is something to strongly consider. So the efficiency opportunity is sealing the ductwork is going to improve the airflow to the occupied spaces, which is where it's important. You also have the potential now to reduce the airflow of the whole system while still supplying the required air volumes to the space, because now that 20 to 30% leakage is now down to maybe 5% or less. That means there's a potential to back off the fan, back off the whole system volume, and still deliver a great amount of air to the occupied areas because the ducts aren't leaking anymore. And this could also avoid the need to actually increase the size of the HVAC equipment. There are a lot of places that are looking at completely replacing HVAC systems in order to reduce the risk of transmission. But ductwork sealing can, a lot of times, get you, all that way there at much less cost and much less time. Now, the tips here, this is one of the only strategies, ductwork sealing, that mitigates COVID, but it can also save you energy over the long term. So it actually has a payback, which can make it easier to justify the investment. Certainly can be an invasive measure, though, depending on the current building condition and the method chosen. Asbestos lined ceilings can be problematic for external sealing, but obviously the inside technology works a little better on that case. This may be also a good time to consider cleaning your ductwork. If there is excessive buildup in it upon inspection. Certainly return ductwork and exhaust ductwork commonly sees those problems. Supply ductwork, not typically as much. But if your ductwork is excessively dirty, what a great time to clean it and seal it all at the same time. Now, the next part of this puzzle is active air purification. So again, this is like the ductwork sealing. This is not new technology, but something prior to this pandemic has typically not been recognized or mass deployed. It was been mostly used over the past number of decades in hospitals and food processing facilities that have high contaminant loads and are really trying to, reduce as much risk as possible due to healthcare acquired infections or, listeria and food processing and those types of situations. So there's a couple different types of technologies we can look at. There's certainly UV light exposure to the airstream. So this is simply where UV lights are put into the airstream. They purify the air passing by. Nobody doubts that, shining UV light on biologics generally kills them. So this is great this can be useful for systems with returned or mixed air. Or we can look at UV light catalytic technology. So this type of technology generates ionic effects and uses ductwork as a dispersant. And this is really applicable to all types of systems. Typical ionic effects include bipolar ionization, as well as photohydroionization, or also called dry hydrogen peroxide. And these type of ionic effects, when pushed into the building, can combat bacteria, viruses, mold, pollen, dust, odors, and VOC. So it's really multi-effective. And it is, certainly not a part of any building code or any kind of ASHRAE standard requirement. But there are technologies out there that are effective. They're laboratory proven, they're real world proven, and they do the job. And they are really going to take your indoor air quality and to the next level while greatly reducing risk. So the efficiency opportunities on this type of tech is to look for UV technologies that utilize LEDs because they're going to have a lower power and a longer life than traditional UV bulbs. Definitely ensure these systems are wired to turn off when the HVAC system is not moving air, unless otherwise recommended by the manufacturer. There are some UV-based systems that are not really, they're not really recommended to power cycle, so they do have to be left on. And look for technology that produces multiple effects, and definitely stay away from any type of technology like this that generates ozone or radicals, because both ozone and radicals are contaminants for the air. They're very effective at killing things, but you don't want to breathe them either. So we want to stay away from those. Next is relative humidity. I think we can all appreciate in Canada, in a lot of areas, we have a very wide breadth of relative humidity levels over the years, right? We have sweaty, very humid, muggy summers, and we have very dry, cold winters. And the research into the optimum zone of relative humidity within buildings is very deep and very old. And the industry standard, as you can see on the chart, is we should be trying to keep the indoor air relative humidity in all buildings between 45 to 65% during every day, every hour of the year. It has, keeping RH in that zone has many benefits beyond COVID-19, including, reduced absenteeism from school and work, occupant mood, productivity. There's all kinds of studies supporting this. Now, if we assume for a second that dehumidification in the summer is usually taken care of by the cooling system, certainly in Ontario, for example, the majority of our cooling load in the summer is latent, not sensible. So we are doing quite a bit of dehumidification in the summer just to get, a relatively good feeling, air quality, air feeling in the building. So usually that's not too much of a problem, but the bigger problem usually is the winter. And the question is, are you injecting humidity? Because if you're not, then your building in most cases is probably too dry inside in the winter. And that's just the fact of our HVAC systems. So the efficiency opportunities here when we're talking about humidity is, if you do have an existing humidity injection system, replacing those old and inefficient systems can be a good choice right now. For example, ultrasonic and high pressure spray systems have come a long way. We typically don't want to install steam humidification systems anymore. And if we do have steam humidification, we may want to consider ripping those out and putting in ultrasonic or high pressure spray. Also verifying that the controls and the monitoring and the overall control sequence of the relative humidity is correctly operating, to make sure that we are controlling to it, the equipment's operating properly, we're not over humidifying or over dehumidifying. So there is a pitfall here though, right? Improving humidity control, can lead to new equipment needed and increased energy usage. There's just in many ways no way around that, especially when we're talking about injecting humidity into systems in the winter. Typically, only large commercial buildings, Class A commercial buildings, have typically monitored and controlled the humidity at the equipment level, and most other buildings just allow it to float. But that can't be the reality going forward. And as I said, there's a lot of benefit doing this, not just for COVID, but for the future and for forever. And the tip here is, maintenance is key. Humidity systems have known to be problematic or not well maintained. So you need to control them well, monitor them well, and maintain them well in order to keep their operation functional. So what we have here is a menu of complementary options. What we went through, we talked about improving the filtration, keeping fans running during occupied times, keeping makeup air systems or economizers at full volume during occupied times. That may not mean 100% outdoor air, especially on standard rooftop units, which are typically only rated for, maybe 20% fresh air intake max. But whatever we can do is going to improve the air quality and mitigate the risk of transmission. Certainly disabling CO2 demand ventilation control, as much as that pains me, we need to think about doing that right now during occupied times, at least again, until the herd immunity and vaccine rollout take effect. Enabling the building flushing pre and post occupied times is a great additional control strategy to reduce risk. Sealing the ductwork, this is one of these only measures that actually has payback in terms of energy efficiency. So it reduces risk today, it pays back on energy over the long term, and it can also create a more comfortable building because we're going to get more regular air supply to all zones. So definitely something, if it's not in your portfolio, to think about. The active air purification, certainly, people want to know more information about that, how these ionic effects like bipolar ionization and photohydroionization work in the air, how they're effective at killing not only COVID, but all other kinds of contaminants in the air, because it's something you can't see or smell. So there's a little bit of skepticism in the market, but there's certainly enough data and studies now to show that technology works. And the humidity control. Humidity control is something we should have always been doing in buildings. But now, renewed focus, trying to do that. And, looking at that graphic on the right, we spend 90% of our lives indoors. And it's actually, very typical that our indoor air quality is not as good as our outdoor air quality. And that's a fact that most people don't realize. I call that effect the IAQ trap. And what it is, and I'm as guilty as this as anybody, is the subconsciously, we walk into a building, and if the temperature is good and we don't smell anything, we assume the indoor air quality is good. The reality is that's not the case, and it's never been the case, and never will be the case. Just evaluating a building on what the temperature we feel and whether it smells or not is no way a good indication of indoor air quality. It doesn't tell us the CO2 level in the air. It doesn't tell us the contaminants in the air. So we need to put the measures in place in order to be able to consistently achieve good IAQ while being efficient. It's the only way to guarantee the health, safety, and efficiency of our buildings. So here's a final slide, and then we'll go to the questions and answers. Just looking at a high-level view of what we talked about here today, and the arrows are indicating for each of the measures. If it's a red arrow up, that means it's probably negative to energy efficiency. If it's a green arrow down, could have a positive impact on the energy efficiency of your building. And the air purification through LED technologies, that's typically a wash. It doesn't really consume a lot of energy, or it doesn't really save energy either. So that's why it's got the two gray arrows, because from an energy efficiency perspective, it's a wash. So thank you everybody for your time, and I think now we're going to go to the questions and answers.
Yeah, thanks so much for that, Jossa. I know I for sure learned a lot. So a little bit, some of it was over my head a little bit. I won't be afraid to admit, but it was really interesting. Thank you for that. So I'm actually going to welcome my colleague Kevin Lockhart, who is our efficient building lead, and he's going to join us here. And I think he's going to come up here and answering a few questions along with Josh. So just a reminder, there are two ways to ask questions. One is you can raise your hand and I can unmute you and you can ask yourself. And then the second way is at the bottom of the Zoom screen, there's a Q&A box. I noticed a lot of people are chatting and asking questions in the chat, but if you could put them in the Q&A box, that'd be really helpful. It just allows us to keep track and not miss any questions there. So there is a question here, Josh, from Hamid, is regarding the UV LED, so specifically for 254 nm, based on what DOE communicated, so the Department of Energy communicated via lighting workshops this week, seems UV LEDs are not still mature enough. Do you have any more data on that subject to share, or can you elaborate? So that's for Josh.
Yeah. So that may be a difficult question to get to the full answer on, not knowing kind of the background of where they're coming from. But certainly, yes, UV light is over a wide range of spectrum, a wide range of frequencies, right? I don't know I don't remember off the top of my head the nanometers from one end to the other, but it is a range, right? So some frequencies of UV light are going to be more effective at killing viruses and bacteria when exposed to them. There's no doubt about that. And LED UV lights generally do produce different frequencies than the traditional fluorescent or other styles of UV lights. I think the key driver here, though, is to think about, am I using the UV light to try to directly kill the viruses and bacteria just simply through exposure? Or am I using the UV light as part of a catalytic reaction in the ductwork to create beneficial ions? That's a completely different application and a completely different way of applying the UV to generate ionic effects, which will then spread into the space through the duct system as those ions are carried down. So certainly would like to explore that a little more, but you really got to look at the UV and the application that you're using.
Thanks for that, Josh. Just Kevin, is there anything you want to add to that, or?
Nothing to add to that. I'd love to bring Josh's attention to Kevin's question, Kevin DeWitt, about duct cleaning. So he's referring to a CMHC research paper that was, I guess the effect was that the standard duct cleaning in residential forced air systems resulted in perforations or holes, and that led to significant reductions in the HVAC efficiency and comfort. Do you have any thoughts on that, Josh?
Well, I'm not familiar with that study in particular, but definitely I've seen duct cleaning done before. I've seen it done manually. I've seen it done with robots in commercial applications. I've seen it done with water, compressed air sprays. There's all kinds of different ways that people clean ductwork. Certainly, some of the more, abrasive ways could certainly punch holes in the ductwork or punch holes in seams, and you wouldn't want that. I mean, given the choice between slightly dirty ductwork and holes in the ductwork, I think I'll probably take the slightly dirty, just me personally. So certainly, I would be very cognizant about the methods that you are using to clean the ductwork, but also consider the fact that if you clean the ductwork, that you can also seal the duct. You should really strongly consider sealing the ductwork afterwards. Even if you don't create any new holes in the ductwork system through the cleaning process, there's still going to be holes in there. That's just typical of the way we've been installing ductwork. So sealing it afterwards can restore the ductwork to really its design conditions.
That's great. Thanks for adding that. There's a question here from Susan. She asks, what about electronic air cleaners for COVID? Do you have any knowledge on that?
Yeah, so there's all kinds of different electronic air cleaners out there. Without going into necessarily all the technologies, I would just like to maybe clarify the difference between active air purification and passive air purification. So passive air purification are any type of system where the air needs to be drawn through the equipment in order for it to be, in order for the COVID or whatever's in the air to be neutralized or captured. You know, examples of those are HEPA filter carts, a lot of electrostatic air cleaners, a lot of them use PCO or photocatalytic oxidation technology, which, you know, they draw air through, a unit, which could be sitting in the corner of a room, could be in a ductwork system, and they do neutralize, contaminants and viruses and bacteria in any of the air that's passing by. Versus active air purification, which is more down this ionic route that I was talking about, where you don't actually need to pull the air through the system. The system is still, the ionic effects are still generated in a cart, or they're generated in the ductwork system, depending on your your building and how they're installed. But they're actually pushing out active ions into the air, which coat all, which, you know, basically fill every cubic inch of the space. And some of them are even effective not just against airborne contaminants, but those ions actually go against surfaces as well. So there really is a fundamental like fork in the road there when you're talking about air purification, passive versus active. And then there's, you know, subparts underneath that, or sub technologies, which fall into one of those two categories.
Thank you. That I'm going to just see if Kevin has anything to add.
I'm following the great questions in the chat. I'd love to see if we could work through those. Josh, I'm not sure if you can see them. There's a question here about flushing the building. If there's a positive COVID case, if 2 hours would be enough to flush the entire building.
That is probably an open question that is very building specific. Certainly, you know, the answer to that question would start with what volume of, if you are going to flush the building, what is the maximum volume of fresh air you can bring in every hour through the HVAC system, and what is the cubic interior volume of the space that you're putting that air into, right? Like how many air changes per hour or fresh air changes per hour can you get in a building using the mechanical equipment that you have? That can vary wildly from different building types. I've worked in industrial plants where they change the air over in a 1 million square foot tall industrial building every 45 minutes. But at the same time, a lot of commercial institutional buildings are not built with HVAC systems that have that kind of volume, especially fresh air volume. So you would need to run those longer to get that same turnover effect. So there's no hard and fast rule. The 2 hours is kind of a general guideline for daily operations. Certainly, if there was a confirmed case, you may want to run that type of setup, the flushing setup, for maybe several hours, maybe even a day or two, in order to mitigate risk as much as you can. There are no certainties. There's only ways to mitigate risk and reduce risk.
So is that the case with, you mentioned a little bit, if there's outside air circulation as well? Because someone in the chat mentioned that schools in BC are ensuring, obviously they have warmer weather there, that ensuring that the windows are open there to ensure airflow. Does that change the results at all, or I guess approach?
It doesn't change the approach. I certainly didn't mention opening windows, but if you can open windows, open windows. There's no question about that. Opening windows is only going to improve the efficiency of diluting and changing over the air in that space. Now, a couple things on that. Opening windows is generally not the best for energy efficiency. You're just going to need more thermal energy out of the HVAC system to maintain the desired temperature. And the other part is, yeah, they're pretty lucky in lower mainland BC, we can't do that in Ontario, right? In the wintertime, especially this last week. But really, like, it's just not an option for the vast majority of the country. But yeah, once the spring rolls around, definitely start opening those windows again for sure.
So Josh, just to add to that, I guess in Ontario or other colder climates, in an ideal world, what we can do is increase the air tightness of our buildings and use balanced ventilation to provide that that fresh air, that would also allow us to control humidity levels. So I think there is a strong tie-in with energy efficiency, but as you mentioned earlier, maintenance of your existing system, and then the same upgrades that you would use for energy efficiency and air tightness will also help mitigate COVID as well.
Mm-hmm. Yep, I would agree with that, Kevin.
Awesome. A question here from Edward is, he understands how humid air can promote bacteria growth, etc. But how does drier air promote bacteria growth?
I'm not going to be able to flip back here. I'm not going to be claim to be an expert on the exact science behind how relative humidity levels affect bacteria, viruses, and everything else you see on this chart here. This is based on years and years of research. But yeah, if you look at viruses in particular, which is the second line, you can see the risk is high on both the, if we have high relative humidity and low relative humidity. That may be due to a combination of effects. Like when we have high relative humidity, there's a lot of moisture in the air, so they're more easier to grow and maintain their integrity, before dying, right? When we have low relative humidity, maybe it's got something to do with the impact of the fact that they desiccate themselves pretty efficiently, but they survive, but in a desiccated state, and that can be reactivated as soon as they touch some wetness, right? So I'm just taking a guess there, but this is based on years of research. This chart may not be the exact chart that ASHRAE publishes, but it's very similar to what has been out there on the market forever. And certainly, I think we can all appreciate, especially on the low side. I mean, we typically do a good job in Canada of dehumidifying our air in the summertime. We size our air conditioning systems to do that, because if they didn't, our buildings would be stuffy and uncomfortable. It's really on the low side that we suffer at. It's not uncommon to see typical multi-res or commercial buildings running around 10 to 15% relative humidity in the winter. It's like because they're just not humidifying, and when you're bringing in that cold outdoor air and heating it up, the relative humidity just falls through the basement. So humidity injection systems, although they haven't been as common except on typically commercial Class A office buildings, they're definitely something we should be considering more and more standard equipment. Awesome.
Thanks for that. And I know you mentioned ASHRAE. They have a lot of fantastic references and reports in there. So be sure to check out the ASHRAE website as well. Josh, I'm just going to get you to flip to the very last slide that you have there, because Josh's contact information is up there. So if anyone has any further questions or would like to reach out to Josh directly, his email's up there. Also, if you don't have a chance to jot it down before we end, feel free to reach out to myself or info@efficiencycanada.org, and we can connect you and Josh directly as well, or with my colleague Kevin Lockhart as well. So thank you so much, Josh, and thanks for Kevin for jumping on to answer a few of the questions. And thank you to our audience for joining us for another discovery session today. I hope you learned something today. I know I learned a lot for sure, and I have a number of questions as well after this. I'm sure others do as well. So just a reminder to everyone, we actually have a break next Friday for discovery sessions because it's the Family Day on the following Monday in a lot of provinces. So we're going to skip next week, but we will be back on February 19th, and we're going to return with Fortis BC, who is going to share details on their natural gas heat pump pilot program. So the results that they're having to date and what's next. So another great discovery session. Thanks again for joining us, and thanks again, Kevin, and thanks, Josh. Have a great weekend, everyone.
Thank you.